Okay, so this is pretty much just about solving exponential equations and log equations. All right, so let's take a look at the ones that we were just talking about, because those are pretty fresh in our mind. So when I said, hey, we can solve these a different way. All right, so let's just say that we have a simple little exponential equation like that. All right. Now you can use a definition to rewrite it as a logarithm. You know, I've said that. That's how you can do it. But you can also use this idea where you're going to take the log of both sides. So basically, whenever you have an x here in the exponent, all right, that's when you want to use this technique. So you're going to take the log of both sides, just like you would multiply or divide or something like that. So we're going to go log of 50 equals the log of 2 to the x. All right, and you can do that. It doesn't change anything because we're taking it to both sides, so the old balance stays even. So now what happens is that our property of logarithm says that this thing, remember, pops out in front. So now this becomes, which makes this problem easy now, because all we have to do to figure out what x is just divide by whatever the log of 2 is. Okay, so if you go into decimals and you go log 50, right, divided by log 2, and it spits out the answer, that's what x is. So you can solve these problems, these exponential equation problems, by taking the log of both sides. So that works, but that only really works when this here is a variable. So when your variable is in your exponent or your power, that's when you want to use this technique. Again, you can use the definition of a logarithm on it too and get the answer, right, like we were doing before. So it doesn't make any difference. You just got to pick what you want to do. I'm not going to say how to do it. I just want you to do it. What's the answer turn out to be anybody punching in? 5.64. Okay, good. So like one of those ones that we had, okay. So we had, let's see, I'm trying to find one. 320 equals 760, negative 0.145, I think it was. So this was one of the problems that I think it was Jessica asked, 0.145H, I think it was something like that. Okay, so here it is. All right. Well, it's best if we divide by 760, so we can try to isolate it, make it simple for us. We could use the log of both sides, but really it's easier to do this first. So let's see. This is 0.4. 0.42. I'm not sure of the 0.45, but I think that's what it was. All right. Okay, now in this case, all right, since it's an e value, heck, we might as well use a natural log because that's going to work out for us real nice. So here again, since that's going to pop out in front because that's our property of logarithms that we learned on Monday.
Do you put it in the front always, or just when you're doing this?
It always goes in front because that's our properties. That was one of our properties of logarithms, right? So it was that third one. So if you have a power, that power always pops out in front. Okay. And the natural log of e is just going to be 1, okay? So this is just 1. I just need the natural log of 0.42, whatever the heck. Well, here we just go like this. Natural log 0.42, okay? Then we'll divide by this thing, 0.45. And there it is. There's our answer, all right? So you could have solved them this way. We use the properties, or we use the definition, all right? But you can use the log of both sides. The log of both sides works, you know, pretty nice on these. I don't even remember what we got for h. Was it, what was it, 5 point something? 5 Yeah, something like that. Okay, so, you know, any other exponential equation when the variable is somewhere else. So like if I had an exponential equation where the variable was maybe here, then I wouldn't want to log both sides because that's not going to get me anywhere. I just assume do the fourth root of both, right? Okay. If it was something like this, you know, if we put the x there, well, that's obvious. You're just going to take 3 to the 6th. Okay. You don't want to log both sides there. So the only time we want to log anything is when this there's my variable in the exponent. Then you can log both sides and it works. All right. But anywhere else, don't bother with it. Okay, so that is solving exponential equations, all right, using the logs of both sides. Again, you can use a definition. Doesn't make any difference. You pick the way you want to do it. You're not going to be asked to do it one way. So solving log equations, and what I'm going to try to do here is give you some variety of what you're going to see in the assignment. All right. So here's one that looks like this. All right, so here we have a logarithmic equation we got to solve for x. All right, notice that the bases are the same. That's always a good thing. All right, we like that. So now what we're going to do is use our property of logarithms. Okay, you just asked about that. So here, this 2's out in front, so that's going to go right there. Okay? So we're going to go backwards. So once we have that, then since these things are the same bases, they kind of in a way cancel each other out. And we're just simply left with this, which means that x has to be 6. It can't be a negative 6 because then it would be taking the log of a negative number. We can't do that. So it has to be a positive 6.
So you don't move the 36 to the front of it since you get to the front already?
Say that again.
You don't move the 36. Oh, is that other?
It's just a log of 36. All right, so you only have to worry about the positive part because you can't take the log of a negative. So, all right, so that's one situation where you're going to have a log equation. But all of these are pretty much going to be all using properties of logarithms. I better stick with this. Remember I said there was stuff that in mathematics that you do things and they don't have much applications, and this is a lot of this. This doesn't, I mean, you're probably not going to have anything in a real life situation that's going to look like this. All right. I don't think I did anything. Yeah, we're not in trouble. I don't, yeah, you're good. Okay. So, let's see. So, we'll use this property of logarithms here. And remember, when it's a plus, what does that mean we're going to do with these things? Yep. You got to get go?
Probably like 5 or 10.
Yeah, go. Yeah. Okay. So, now we're going to use the definition on this. Okay, so here's our base. So what would this look like if we used our definition? So what's the base? 5, right? 5 to what power? First. Okay, equals all this stuff, right? Output becomes the input. Good job. Okay, there we go. Okay, so now we just have to FOIL this. Okay, x squared, 2x, 6x. I'm sure you probably can do that. FOIL it, okay. All right, so I'm going to kind of stop here for a second. So this is what we got. So we started with this. We used, since it's a plus, we know that those two things are going to multiply. The bases are the same, which is a good thing, because if they weren't, we couldn't do any of this. All right, so we put these things together. We're using the definition again. See, the definition is so big. We use it a lot. 5 to the first 5, multiplying these things. And now all we got to do is solve this. Okay, so it's a quadratic, so that means I got to move and set it equal to 0. All right, and to solve these, you use quadratic formula. You could graph it, but this one just factors. And the ones that they in the book, they should really all factor. So in case you forgot how to factor, you're going to take this 7, right? Find multiples of factors of 7, sorry. There's only 2, 1 and 7. And they got to add up to 8. So those are our only answers though. So So that means that x is going to be, I don't need an equals there, x is going to be -1 or -7. Now, chances are one of these isn't going to work because I see I have two negatives, so I get a little bit concerned as to, oh, wait a minute, I can't take the log of a negative. So I'm going to just kind of scroll back up here and see if any of these, when I put -1 and 7 in there, okay, if I have any issues. So -1's okay here, -1's okay here. I'm going to get both positives. But if I put -7 in this one or this one, we get negatives. So we pitch the -7, and the -1 is the answer. Okay, so we're going to cross this one out, and that's the one we want. Okay, so there's ones like that. Let's see if I can find some more. A lot of them are just pretty much the same thing, but there was a couple of them here. Here, let's do one like this.
So that what we just did, if we were going to graph it, what would we be looking for on the graph?
Graph it to solve it?
Oh, okay.
Is that what you're saying?
Yeah.
I'm not sure this would be a good one to do that way.
Okay.
So what you would do is type this in one of the lines in the decimals, right? Put your 1 into another line. So you have this would be
so
like
you have things that are like intersecting.
and they're going to intersect.
Okay.
Yeah. It would probably be a good way to check, I guess. It really kind of depends if what those graphs are going to look like. It might be a little bit confusing, but you can try it, you know. Yeah. Okay, so let's look at this one. All right. So how are we going to rewrite this thing using the properties of logarithms? What's it going to look like? Let's see if we can work through it. I know I'm going to have this. Well, what am I going to take? What is this end result going to be for the log? Yeah, x plus 4 squared. Good. Because this 2's got to pop out in front there. And then what are we going to have? We have a minus, so that means divide by what? What are we going to divide by? 9 is equal to, that doesn't change. Okay, so again, see, we're just using the properties that we learned Monday on these. Okay, and now we got to use the definition. Okay, so let's use the definition. So if I use the definition, what am I going to write? 3 to the power of 2 is equal to, yep, right. Okay, so now I just got to do a whole bunch of algebra to get it figured out. Okay, and it's going to be pretty much the same thing that we had. All right, so you either multiply by 9 or cross multiply, whatever you want to do to get the answer. So here's my equation that we got to solve. So we just go x squared, 8x, 16 equals 81. So we just FOILed this out. Okay. Yeah. What happened? Can I go up?
Yeah, go up to the first equation. Is there a reason why we can't simplify negative log 3 and 9?
No, you could. I didn't think about that.
And the second thing, shouldn't we square root x plus 4 squared and square root 81 at the bottom? So we get x plus 4 is 9.
Gosh dang it, Jonah, you're absolutely right. I didn't think about that. I'm so into doing it this way. Thank you. That's a great idea. So he's saying instead of doing this, which would have been a real waste of time, thank you, let's just square root everything. So this is going to be a plus or minus though, and then subtract 4.
You know it's going to be a plus or minus.
How do I know? Because when you square root a number like this, it could be -9 or +9, because -9 squared is also -9. But one of those is going to get, again, you can't take the log of a negative, so see how the -13 isn't going to work, because that's going to give us a negative in this first one right here. It's going to give us a negative there, so we're going to pitch that one and stick with the 5.
Also, why in the beginning did you divide it by 9?
Why do we divide it by 9?
Yeah.
Because the property of exponent says that we have a minus here. Okay, that means you're going to divide these two quantities.
Oh, and then the log 3 cancels out.
Yeah, there's 2 new slides down here. Yeah, so whenever you have a minus, that means you're going to divide. Plus, remember, you're going to times. So that's pretty much everything that's in that section 337.
What was the solution for that last one? Because it comes out to 9 equals plus or minus x plus 4. Or plus.
So we're going to get a 5 or a -13, right? And -13 is no good to us because we put a negative. If we put a -13 into the x plus 4, here, we're going to get a negative. So that's why we pitched that. But 5 works out okay.
So it's plus or minus 9, and then that just equals x plus 4.
Right, and then you subtract 4 from both sides.
Okay.
But again, the -13 is no good. I'd be really, if you get negative numbers, then you probably want to check them because they're probably not going to work. You can't take the natural or log of a negative. And I'll give you some of these to work with too when we do our practice stuff. Okay, so let's take our break now, and then we'll do 4.7. Talk about money. So 4.6 we did. 4.7 is about applying basically exponential equations to money. I'll just call it functions. All right. So there are different types of, everybody's had a loan of some type, right? They might probably have car payments or house payments or whatever. All right. So those loans can be approximated by using some of these formulas, but they're not going to be dead on, okay? Housing, as you know, is a whole different ballgame. That's an amortization loan, all right, which is a pretty complicated, actually, mathematical formula because of the way that the amortization, where it pays off the interest and then pays on your principal, all right? Usually the best way to figure that out is to just use some Excel type of spreadsheet. Some of you may have done that, played around with that kind of thing. Or, you know, there's online sites that will say, you know, hey, what do you want your monthly payment to be? La-di-da-di-da. All right, so that's not even going to be part of this, okay? But for some of the loans or investments that are out there, they use some of this stuff. Credit cards are pretty good examples of that. So, as you've progressed through school, you know that there is something called simple interest. All right. So this is just a real simple interest formula where I is simply equal to PRT. All right. So I is the interest. This is the principal. And this is the rate. And this is the time. All right? Okay. So that's like the very simplest interest. So if you wanted to, if you had, you know, $500 that you were loaning, okay, and the rate was 3.5% or something like that, that's a pretty good rate. And the time was, you know, 3 years or something like that. And this is an annual rate, so then you just 500, okay, make sure you change this into a decimal. And then that gives you the answer, okay? So, I mean, that's just real basic interest. Okay, simple interest formula. All right. Okay. I think it did have a car guy tell me, a loan manager or something. Oh, all we do is use simple interest. Nah, I don't think you do because I figured it out. It wasn't the same. All right. So, however, most of your loans and your credit card stuff is different. All right. They use this formula. Okay, so this, so P again is just the principal. All right, R is the rate. N is, we say, the number of compounding. And T is the time. Okay, A is the amount of what the loan is. All right, so P is your principal, R is the rate, number of times compounding for N, T is the time. What does it mean by number of times compounding? Well, like, they'll tell you how many times it's being compounded. Most things are going to be 12, right? One every month. Okay, so that would be monthly would be 12 times. Okay, some loans are semi-annually, right? Twice a year. Not many, but some. Okay, there's a quarterly. All right, there is a number of different things. Most of the time, though, it's going to be 12. So here, let's say we're going to do the same thing. So let's say we're going to go with $3,000. Okay, is what we're going to look at here. Okay, our rate we'll say is 5.5%, something like that. All right. T, we'll look at it for 3 years. And we'll say that it's compounded monthly. So the problems that you're going to have, that's what they're going to look like. They're going to say, well, you know, you've got this amount of money, and, you know, it's a loan, and you're going to compound it, and here's the interest rate, and la-di-da. So we put this in, all right? So A equals 3,000 is the principal. That's going to go there. All right, 1 plus, okay, R over N. So I'm going to make this into a decimal by moving that decimal twice. N is the number of times it's compounded, so that's 12. 12 is up here again, and then 3 is the years. So we're just putting these numbers in and figuring it out. So best thing to do is just dump that in the decimals and see what it gives you. Now, when you put it in there, make sure you put parentheses around these things, or else it isn't going to do it correctly. All right? I'm going to try my calculator and see what I get here, although it doesn't work real well sometimes. So this says 3536.84. That seems like that's probably right. Okay, did anybody try that, putting that in decimals? Did that come out to be that what it is? Yeah? Okay. So then that means that if your interest, you know, this would be how much you're paying in interest right here. Okay, over that span of time. All right. So the A is just gives you the total value or the total amount of the loan. Right? And of course, this isn't making any, you know, payments on it kind of thing. So if we wanted to know our payment, then we would just take this guy, of course, and divide it by 36, and that would tell me what my monthly payment would have to be to get that done. Okay. So that's how that interest formula works. Okay, so what we're going to do is look at a very basic, using that and then looking at different types of compounding rates. Okay, so but I'm going to have to get the decimals to do that. I'll have to switch to this. There we go. Jump into here. Okay, so let's start with a very simple compounding interest scenario. So we're just going to go with $100. Okay, parentheses 1 plus, just make the rate 5%, so it'd be 0.05. Okay, divided by, let's do it annually. So that means it's only compounded once. Okay? And I just want to know that for 1 year. So I'm just going to put a 1 there. All right? Very simple. It's going to cost me $5. All right? Which we could have figured out because it's only going to happen once a year. All right? So if we change this now to something different, maybe twice a year, which means this is going to also have to be twice a year because it's 2 times 1. Okay. Well, not a whole lot different. All right. Let's try monthly. A little bit different. But let's do this. Let's say, actually I'm going to leave these, I'm going to leave this up here because I want to show you something. Okay, so now we got that. I could have put a slider in here, but I like doing it this way. Okay, let's try this. So we did monthly. Let's try daily. So what would I put down here for that? And when am I going to take it to what power? So you would think, wow, you're raising that to a 365. That's going to be a huge number. Well, look what happens. All right, it's really not a whole lot significantly different than this. All right. So let's try this again. Same rate, not changing anything there. All right. Let's go hourly. So that'd be 365, and how are we going to get it to be hourly? Times by 24, right, good. Okay, and then we're going to raise it. Again, you're thinking, man, that's just going to be a huge. See how you got to put a parenthesis up there? I did that on purpose just to show you what happens. I truly did too. All right. So, and we're raising it to a huge number, but we're still not gaining anything here. All right. So that's just. There we go. Okay. So we did daily. Let's try by the minute. So that'd be 365 times 24 times. So that's hours. So now what are we going to multiply by? We got to get, what did I say, seconds, right? Minutes. We can go minutes. So what are we going to multiply this by? 60. Very good. Now that's 61. Okay, and then we're going to put that up there. And you'd think at some point, and it's just going to jump up. Well, I did that again. That time I didn't do it on purpose. I just forgot. Okay, it's still not making any really significant thing. So there's actually, if we did this and we said, well, we're going to do it by seconds and it's, milliseconds, whatever, it becomes that's still the same kind of number. All right. So why is it that this isn't changing, even though we're making this such a huge exponent power here?
You're dividing by the same amount.
Yeah, we're dividing by the same amount, right? So we're taking this here equation. Okay, so we're not changing anything. So we have this 0.05 being divided by such a big number that it's so small that even though you're raising it to a power, it isn't making that much of a difference. All right. So watch what we do here. So we're going to go like this. Okay. We're going to go and put this formula in. So we're going to go 100, okay, times E. That's our famous E number. All right. To the, what was our rate? 0.05. Okay. And times 1. See, once again, gosh dang it. Well, it doesn't make any difference because it's just going to be that. Notice that these things are pretty much the same. Okay. So when you have something, when they say compounded continuously, then you're going to use the E value. All right. Anything before continuously is using the other formula here. All right. So problems that are continuously, we're going to use E. Anything else, we're going to use these. All right. Along with this. Okay. So let's go back up to the monthly one. So here's my monthly. All right. 105.11612. All right. Years ago, this is quite a few years ago when credit card companies were kind of taking advantage of people. So they would report a certain rate. They would say, well, you know, it's only 5%. But what was happening is that is not necessarily true. So if I take down here, and let's see, that was 105 point, what was it, 1 for the monthly one? 1.
Yeah.
Okay, and I divide that by 105, okay, not 105, 100, sorry. Okay, I get 1.0511, okay? So, this is your rate, because the 1 just means that it's being added to, right? So there's the 1 plus our rate, okay? So the rate was actually 5.11%. That's how much interest you were paying, okay, over the course of a year. So then that's where APR comes in, because then they had to start reporting what the annual percentage rate is. So there was a difference between the rate and the annual percentage rate. So when you get credit cards now or other loans, they always say, well, this is what the APR is, because the government said you had to do that. So they were misleading people, right, into thinking, even though this is, well, it's not very much, right, it's 5.11%, but if it was a large amount of money, it was making a difference, okay? So that's why you hear APR now rather than just a rate, okay? They had to change it, all right? So I wanted to make sure you saw that. Let's see. So that's pretty much all there is with that. Let's go back here. I'm going to switch back to this guy, all right? And here we go. So when we have continuous, I missed a U. Bless you. So here we go. When we have continuous compounding, you want to use this formula, A equals PERT, all right? And, you know, a long time ago, when I learned this, it was a long time ago, it was PERT. And it was easy to remember that because there was some shampoo out there called PERT. I don't think it's around anymore, but anyway. When you have continuous compounding, you're going to use PERT, okay? P-E to the R-T, all right? So either you're going to have some sort of a rate and a compounding, or you're going to have a continuous. So I'm looking here to see if there's anything. I think they showed a couple other things in here, present value formulas, okay, and what was the other one they did? Effective rate of interest. I didn't give any of those problems. I looked to see if I did, and I didn't. So all the stuff that I did was all basically using this formula, okay, where all you're going to do is substitute values in, all right. Let's do one more thing here, okay. This was kind of interesting. Okay, so how long will it take to double an investment? All right, so let's come up with, let's say we're going to invest, you know, $500 or something like that. All right, and you know, you find this great thing that's going to give you like 5.25%. Nice. All right, okay, and we'll say that they're going to compound that. Okay, so we're going to use this formula. And let's see, this is going to be 1. The question is we don't know what t is, right? But we do know that since we want to double it, that's got to be 1,000, okay? So we don't know what t is. We want to know how long it takes to double it. It's just going to be compounded once a year. That's it, all right? So let's try this out. So first, we're going to divide by 500. And we can't distribute this because I don't know why I'm putting it over 1. You don't need to, but there it is. All right. Now look, this becomes an exponential equation, right? And you know how to solve this now. You can use the definition or you can log both sides, right? So you got to pick your way. The way it works for you, I don't care. I'm just gonna ask you to solve these. So you're gonna pick your way. So let's say you like the log things. You go, I like that log thing. I'm gonna do that. Okay. So we'll put the log in there. Bring that down. So then the time is gonna be whatever the log of 2 is divided by the log of this 1.0525 thing, okay? So somebody use Desmos, tell me what that is.
1.64. I'm sorry. No.
I was gonna say that doesn't take very long.
13.5.
Okay. All right, since we're only doing it once a year, it's going to take that long. All right. Now, what's interesting is there's something called the rule of 72. Okay, which basically says if you take 72 and divide it by the interest rate, which was 5.25, that will approximate how long it takes for something to double. Okay, it's just an approximation. I can't even tell you how come it works, but it usually does. All right, so if I take 72 and divide it by 5 1/4, 13.7, pretty dang close. Okay, it's called the rule of 72. All right, gives you an idea how long it takes to double something. And it works, you know, for most cases. But it's not exact science, okay? It's just magical. I don't even know where it comes from. So here, again, if you want something to double, okay, you're just going to use that. All right? And even if the question is how long does it take for something to double, you can put any number in there that you want. It really doesn't matter what you put here, because when you double it, this is always going to be what? What number is that always going to have to be? 2, right? So it really doesn't matter what you put here, because when you divide it, you're going to get a 2 there anyway. So who cares? You just 2. If it's going to triple, then you'd have a 3 there. All right? It really doesn't matter. Okay. And that's pretty much all I had for the financial stuff. Do you have any questions? Do you want me to do any more? Or I'll give you some to practice, but. I think the ones that I had that kind of messed people up a little bit was just figuring out what the interest was on them. So as long as you remember that, like up here, that when you get this A value, that's how much the total loan is, and that the 536.84 is actually your interest, and you're okay. All right. And again, this is, I mean, it's not, I don't know how applicable it is to most cases, like your car loans and stuff. I think that they use a little different, because I've used this before and it never works out right. Okay, and they just tell me, oh, it's just simple interest. And I don't think it is. Okay. So anyhow. So let me give you some of these to try out, and then we'll take our quiz here. So on page 337, let's look at 11's a pretty good one. One's a good one. Um, 47. We'll do one of these. I think that one's part of it. 346. That's a 4. Oh boy. Oh, I do a present value one. So I'll put that on there. Rate of interest. Did I do that too? Oh, well, that one's okay. 26. So 22 is one that we need to go over, but we'll just do it when we get to that point. So you might want to save that one. So what is that, about 6 or 7 of them, I guess? You can look up 22 if you want, but we can go over it too.